Start with a problem. Say you're a survey officer at a spaceport and the government comes to you asking for census information. Your task is to tell whether an arriving passenger is human or alien. The only thing you have access to is their height and gender, which is automatically registered upon entry. Because you're lazy, you decide that instead of standing behind a desk and determining this by hand, you will create a mathematical method of determining this important information. To start, you need data, so you put out a survey asking for the height and gender of all your colleagues and get back the following information. Note that males are colored red and females are colored green. If we chart this data, we get the following graph. How we approach this problem will depend on our assumed knowledge of the world. For example, we could assume that height is independent of gender, and that heights will assume a bell-shaped curve, which I will from here on in refer to as a Gaussian. For more information on Gaussians, I have placed recommended readings in the description, but for a simplified summary, a Gaussian models the bell-shaped distribution over all real numbers, so from -infinity to infinity. In the one-dimensional case, a Gaussian is described by the following equation. This formula describes the probability density at a specific value of x given the model parameters mu and sigma squared. Mu corresponds to the mean and sigma squared corresponds to the variance. Note that this is not the probability of the height x. Continuous distributions like this will always return 0 for random variables equating a specific value. To get a probability, you would have to integrate under the PDF. This is why the PDF is called the probability density function. If you vary x and plot the corresponding outputs for a Gaussian of mean 0 and standard deviation 1, you will arrive at a familiar shape for the PDF. This would be a great help in answering our original question. As soon as a passenger arrives to our desk, we would check their height. If their height belongs to a region of high probability density of our Gaussian, then we would say that they're human. So let's do this. First, let's define our assumptions. Assumption number 1, heights are independent of gender. Assumption number 2, heights are distributed according to a Gaussian. I'll keep these assumptions in the top left for the rest of the video. It's important to always know your assumptions when you're modeling. This is to ensure that you make your decisions in a rational manner based on your assumptions. The question still remains though. How do we find the optimal values for mu and sigma squared, mean and variance? Well, in this case, we can use something called maximum likelihood estimation, or MLE. Before we do that, let's quickly define what a random variable is. I've alluded to this already in this video. A random variable is a variable whose value is determined from the output of some random phenomenon. This is not a formal definition, but it'll suffice for our purposes. We will denote all random variables with the letter x. Related to our specific problem, the random phenomenon describing the random variable is heights, which we assume to be modeled by a single Gaussian, with the yet unknown parameters mu h and sigma squared h. Please note that we are defining random variables x to be defined by a Gaussian parameterized by mu and sigma squared. As such, when we say we want the probability of a random variable x taking on a specific value x, we write pxx, or equivalently px equals x. Note that in a continuous distribution, px equals x will always equal 0. I have mentioned this before in this video. if we want to get a probability or a meaningful probability, we will have to take a range, like px is less than x. In a discrete distribution, the PDF will become a PMF, in which case px equals x will return a meaningful probability value. Now, this has all been a very informal explanation of random variables, but for the moment it will suffice. Going back to our problem, we have 8 points in our dataset. The point of MLE is to find the distribution parameters that maximize the probability of seeing all of the data points. We already know the formula for a single point, but we need to find a way to extend this to find the probability of multiple points together. To do this, we need to make an assumption on our data, namely assuming that they are independent and identically distributed, IID. This is a very important assumption in statistics and states that we can represent each data point with random variables x1 to xn. All of these random variables are identically distributed with the Gaussian parameterized by mu and sigma squared, the same Gaussian. Additionally, they're independent, meaning that any one random variable does not affect another. Now, this assumption can be easily broken. For example, if we got all of our data from the same family, it is likely that all of their heights are similar. And all of the independent variables are going to be interdependent to some degree. But let's assume IID in our case. This means that the probability density of all of the data points can be described as the joint probability density function shown here. Because we know in the independent case that none of the variables are interdependent on each other, we can separate this as the product of the individual probability density functions for each random variable, as shown here. This is similar to saying, what is the probability of getting 2 heads in a row if you are flipping an unbiased coin? If we assume each coin toss is independent, then that is just the probability of getting a heads on the first toss multiplied by a probability of getting heads on the second toss. 0.5 times 0.5, 0.25. Now, be careful to think about this assumption when modeling, as if there are major dependencies between random variables, you may need to use a more powerful model incorporating these conditional probabilities. To get the total probability in our problem, assuming IID, we're going to take the product over multiple Gaussians, as we've talked about before. So starting off at the joint, we split it up into the individual components. We replaced each component with a Gaussian and we multiply them all together, and we get the following. Now, this describes the probability or the likelihood function that we want. And to find the values of our model, the parameter values of our model, we need to find, or we need to somehow maximize this joint likelihood function. Mathematically, this can be formalized as the following argmax. Now, this is a problem that can be solved using gradient-based optimization. From calculus, we know that we obtain a critical point when the gradient is 0. We can then check the curvature of the point using the second derivative test and determine whether that point is a maximum or a minimum. To make the derivative easier, we will maximize the log of the likelihood function instead of the likelihood function directly. To see why we can do this, we need to think about what we are doing. We are trying to find the arguments that maximize our likelihood function. As such, if we apply a transformation like a log to our function, and the optimal argument values will still map to a maximum, it is still a viable transformation. Now, a logarithm is known as a monotonically increasing function, meaning the function increases as the argument does. Because of this, the ordering of the points will be maintained, and the maximum of a certain argument in the original function will still lead to a maximum in the log function at the same argument. Hence, we can write the argmax of the original function is equal to the argmax of the log of the original function. Now, let's optimize this new function using the gradient method. The steps are relatively elementary, so I will not go through them. However, I've left the working out on screen. The main concept remains the same. First, let's take the logarithm of the entire function. Then take the derivative of the logarithm and set it equal to 0. Then solve for the mean parameter. And we get a final value of 164.89. Next, let's do the same thing to obtain the optimal variance. Take the log, take the derivative, set it equal to 0, and then rearrange to solve for the sigma squared value. Here we get a variance value of 121.05. So these are the two optimal parameters for our model. Since we know we're modeling a Gaussian and the minimums will occur at the positive and negative infinity values for the height, we do not need to do a second derivative test, as any finite value for mu and sigma squared is guaranteed to be the maximum. Another way to think about this is that the Gaussian is a monotonically increasing function until it reaches mu. As such, the logarithm of that monotonically increasing function will lead to a strictly concave function, as log is a strictly concave function. Because of this, and you can see it here on this graph, the solution of the first order derivative is guaranteed to be a maximum, and we don't need to do anything more. Proving that the second derivative is negative is more involved because it'll require us showing that the second derivative, in this case it'll be a Hessian, of the log likelihood is negative semi-definite. Doing this is out of the scope of this video, but I will make a separate video on this and link it in the description. We can now use this model to find a probability of whether an arriving passenger is human or alien based on our model. I would just like to point out here that these formulas can be easily extended to any amount of data points. If we say we have n data points, then the optimal parameters will be given by these two formulas, which mirror the ones we derived earlier. If we plot the probability density function of our model, we can see it encompasses all of our interviewees, with the Gaussian centered at the mean. Now let's take a step back and look at what we've done. We have used a sample of 8 humans alongside several assumptions to model the distribution of heights for the human population. Now we can set a threshold based on this distribution according to our boss's requirements. Let's say the requirements are that there's a limit on how many humans you can wrongly classify, set to 10%. We know from elementary statistics that 2 standard deviations will account for about 95% of the data. So this would meet our requirements. To find these bounds, we can just use the standard deviation. The upper bound is mean plus 2 standard deviations, giving us 186.89 centimeters. The lower bound is mean minus 2 standard deviations, giving us 142.89 centimeters. If we plot these bounds on our graph, we get the following shaded region. Note that this will account for approximately 95% of the distribution. To deploy this in practice, we set an automatic thresholding switch. If a passenger comes in and their height falls outside of this region, we will classify them as an alien. Otherwise, we will classify them as a human. If we wanted to be more sophisticated, we could have used confidence intervals to create our classification thresholds. But we shall leave confidence intervals for a future video. Before we finish, let's go over the potential pitfalls we could encounter with this model. First, we assume that our chosen dataset was large enough and representative enough of the human population. If this were a real-world scenario, this is definitely not the case, but we will cover minimum sample sizes in a future video. Second, we are assuming that it will be okay to filter out any outliers. Humans come in many shapes and sizes, and we must be prepared to occasionally misclassify. Third, we are assuming that human heights are unimodal and are well represented by a Gaussian. If we have kept those in mind, great. We deploy the model and we win Employee of the Day for our tireless efforts. However, we soon find out there's a big problem. The model has been consistently misclassifying a specific type of alien as human. What's going on here? Let's find out in the next video.